So Professor Anoop Jain is an assistant professor at IIT Jodhpur. He did his BTech in 2009 from Krishna Institute of Technology from Ghaziabad. After that, he completed his MTech and PhD in ISC Bangalore, India. From 2017 to 2019, he did his postdoctoral fellowship from Technion, Israel, and he was funded by Lady Davis Fellowship. His research interests include cooperative control of multi-agent systems, event-triggered control, cyber-physical systems, and non-control theory. With that, I would like to invite Professor Anoop Jain to give the talk. Thank you.
So, good morning, everyone. I hope I am audible clearly. So, thanks, Amit, for the nice introduction. And it is a pleasure to speak at this special occasion. And other parts we will take in the reminiscence. And this is actually all effort goes to Professor Ratnu. I must thank him and his team for the nice arrangements that they have done. So today I will be talking about geofencing control of multi-robot system, the work that we are recently doing. So this is the work with my PhD students who I'm seeing. So the motivation of this problem came from various application of autonomous systems in various safety critical mission. For example, while surveillance across the boundaries of two countries or a state, we want the motion of the vehicle to be restricted. Similarly, like doing some exploration task inside any tunnel, we want that the motion would be restricted so that it avoid colliding with the walls. So these are the applications where you want the boundaries, the motion would be restricted within the outer boundaries, but there are applications where you also want that the robot should maintain some kind of safe distance from some kind of target. For example, while tracking a hostile target, your robot must maintain a safe distance from it at all times. And similarly, there are other applications like firefighting, where this drone should maintain some kind of safe distance. So geofencing control is actually very important problem in present application scenarios. And let me now formally define that what is this geofencing control. So geofencing control of autonomous unmanned robotic vehicles is a technique that uses virtual boundaries to restrict or prevent them from entering into certain areas. So there are several applications, some of them I have already discussed in the previous slide, like surveillance, tracking and monitoring, search and rescue, target encirclement, and source seeking applications. So I actually began this work with Professor Ghosh during the last year of my PhD. So where we solved this simple problem. Our objective was that there is a team of UAV, have to bring them on this common desired circle, and at the same time that you want their boundaries, trajectories remain bounded within this boundary. So our objective was basically threefold. That is written here. We want the motion around a common desired circle, and we also want to arrange the vehicles on this desired circle in some specific formation, and at the same time we also want that their trajectories remain bounded within some boundary. So actually in solving these problems, we exploit the idea of this barrier Lyapunov function. So this is like one expression of it. This is called as logarithmic barrier Lyapunov function, where this term delta, this is actually the separation between the two boundaries, and Ek that is appearing here, it is nothing but the position error of the kth robot from the desired stabilizing point. So I actually began the problem from here, and later we also explored that what kind of patterns we can achieve on this desired circle. So that we classified as Mn patterns. So N refers here the number of agent, and M is nothing but the number of groups in which we can arrange them. So this is something like 1-4 pattern where 4 agents are there and they all are moving together on this circle. This is the 2-4 pattern in which they are arranged in a group of 2 at equal angular separation, and the other one is 4-4 pattern in which there are 4 groups of agent at equal angular separation. So this is actually referred to as synchronized formation. This is splay formation, and this is kind of, we say, balance formation. So actually the splay formation is nothing but a special case of balancing. Okay, so in today's presentation I will not focus on these different kind of phase patterns. Instead I will discuss more into this geofencing control problem. So we have actually also extended the problem to achieve these kind of formation on more general class of curves. So these are the polar curves in which so these could be of either like convex or non-convex curve, and we can achieve some kind of formation around them. And what we can see that the trajectories of the vehicles are actually limited from this external boundary, which is shown in the red color here, and there is also some kind of inner boundary. You will also remain outside that. But the main thing here in these problem is that the nature of this external boundary or the internal boundary, it is actually the similar of the stabilizing curve. Okay, so even in this circular case you can see that we want to stabilize on this desired circle, and the nature like this external boundary is also circular, which is also concentric with the stabilizing curve. But in practice we do not have such kind of scenario. The nature of the boundaries and even the stabilizing curve could be different. So I will discuss that practical scenario or more generic scenario in a while. So in all these works I have considered what is referred to as unicycle model of the robot. So it is like the simplified model of most of the practical robotic system. Okay, so this is like a unicycle robot in which you can actually control its speed by pedaling it, and you can also control the angular rate. Okay, so this is the kth unicycle robot. In the planar space, v is its linear speed, and theta k is referred to as heading angle or the velocity direction, and omega k is the turn rate that like we can control. So if you take the velocity component along x and y direction, you can write down the equation of motion in this way, and theta k dot is turn rate, which is nothing but your control. So in all these works we have taken the assumption that the robot is moving for the constant speed, which is also required for better fuel efficiency and endurance, and this control omega k that we want to design to fulfill our objective. Okay. So more concisely we can also represent this model in the complex form. So this is the complex form where r is nothing but the position in the complex plane. So this is nothing but x plus I by, where I is the complex number. So the same, these two equations can be written in this way, e to the power I theta, and theta k is your control. So I will discuss the use of this model subsequently. And one thing that is important here, that if your turn rate, that is theta k dot, if your theta k dot is positive, so basically this angle theta k will be increasing, so it shows that the robot is moving in the anti-clockwise direction. When theta k dot is negative, it shows that it is moving in the clockwise direction. So now coming to this problem, what if the safety set is arbitrary? So this is one of the example where you can see that the outer boundary is no more a circle. Okay, so there are various challenges that we encounter in such kind of problems. First of all, non-uniform radial separation. So the separation between the two boundaries is not uniform anymore. It is non-uniform. Second thing is, like, this desired curve and the boundaries are not necessarily concentric. So although in this figure you can see that they are concentric, but they are not necessarily concentric. They may be somewhere, center could be somewhere else. And of course, that we have this non-holonomic robot constraint. So basically this unicycle model, it cannot directly move in the this lateral direction. So that poses like these are called as the non-holonomic kinematic constraint, and because of that we also have some kind of challenges here, and also like presence of external disturbance that also cause a lot of problems. So for example, when we are talking about operation in for UAVs, so this wind creates a lot of problems, so we should also be taking care of that while designing our controller. So what is the problem of today's talks? So in today's talk I am discussing even little simpler thing, that now the two boundaries are not concentric. You can see that their centers are different. They are actually non-concentric circles. So this is your desired circle on which you want to stabilize the agent, and this is the boundary which is non-concentric with this circle. So even in this kind of setup, you can see that this radial separation delta, this is actually dependent, spatially dependent, because you can clearly see if you move in the space, delta varies. Okay. And so what happens if you design this in a classical control way, this derivatives of this delta somehow appears in this Lyapunov function derivative, and it leads like indefiniteness of the Lyapunov derivative. Okay, so we need to think of some other tools to handle it. So, and also suppose somehow if you are able to design the control, you will require the continuous time feedback of this, the rate at which it is changing. Okay. So we thought of some different kind of approach in which we can actually transform two non-concentric circles to concentric circles. So in the transform plane you have basically the uniform spatial constraint. So that I will discuss in a while. So actually when we talk about application of such kind of consideration in the arbitrary shape boundary, so this can also be considered, because like you can see that you can always fit this non-concentric circle which actually touches any arbitrary shape boundary. So unlike the concentric part which you can see here in the adjacent part, you will have more space. So your vehicles are having more space to maneuver and they can do the task effectively. So the outline of today's talk is, first I will discuss the solution approach that actually relies on the idea of Mobius transform from the complex analysis. Then I will discuss some of its interesting properties that we have used to solve this problem. Then control design in the transform plane and how we can actually achieve the control in the actual plane, and followed by simulation and the experiments. So this is our solution methodology, that we actually want to transform these non-concentric circles to the concentric circles. So in the transform plane you can see that this radial separation is actually uniform. So here is one interesting point, that is although obvious, that it is motion mapping, it is not just a position mapping. So what does it mean? That we are not just transforming the position of the robot, we are actually transforming the complete motion, means its velocity, heading angle and the controls. So everything will be transformed. So it is something like that. This is your actual model, and you will transform everything to the transform plane, and you will design the control in the transform plane, and then you will go back to the actual plane. So what happens when you go to the actual plane? There may be some kind of feasibility issues that appears in the control thing, but Mobius transform does not show that. I will discuss that part. Okay. So the main question here is that what is this transformation which actually does this job? So this is actually given by this what is referred to as Mobius transformation. So this is a very nice photo of him which I got from internet. So he is actually a German mathematician and an astronomer. So he has given this Mobius transform of this form, so which actually transform one complex plane to the other complex plane, and A, B, C, D are some complex parameters, and this quantity AD minus BC is non-zero, because if it is become 0 then it is meaningless. For example, this could be 0 when both C and D are 0, so in that case this has no meaning, right. Similarly, if you take the case when let us say A is 0 or C is 0, then in that case also it will become a constant. So that is also not very useful. Okay, so this is one of the requirement, and which is called as the determinant of this Mobius transform, analogous to matrix we have. So the domain of this transform is complete complex plane except this point minus d over c if c is not equal to 0, and if it is your c is 0, then the complete domain is like it is complex plane is the complete domain. We can also take the derivative of this transformation with respect to z, and which is given by this thing, and it is also well defined because we have AD minus VC non 0, and this is actually a conformal map. So I will discuss that what is that. We can also take its inverse. Inverse is also like given in this way, and this is also having the same determinant, and the domain of this inverse function is this thing, and this is also a Mobius transformation. So basically, if you see that this Mobius transformation defines a bijective and holomorphic map. Holomorphic basically this is analytic map from one domain to the other domain, and that's why it is also called as bilinear transformation. So I will just quickly go to see its property. So there is one interesting property that Mobius transform actually maps circles to circle, and I read in some of the very interesting book that this is the only transformation which actually does that. So there is a proof, formal proof of that, and I have discussed in the previous slide, Mobius transformation are conformal. Conformal means that if there are two curves, and if you map those two curves in using the Mobius transform, the angle between them is preserved. Okay. Other interesting property which is actually useful for us is this symmetry principle. So what does it say? If two points are symmetric with respect to a circle, their images are also symmetric with respect to this Mobius transformation. Okay, so what is this symmetry? Basically we understand, so these 2 points A and B, they are symmetric with respect to this line L, okay, and by some transformation through this M, we got respective points A tilde, B tilde, and this is the new line L tilde. So these are also like symmetric with respect to this image L tilde. Okay, so similarly, the Mobius transform also does the same thing. Let us say this is K is your circle, and with respect to this circle, 2 points A and B, they are symmetric. So in case of circles, symmetry has a different meaning. It is not like equal distance from this line. It has a different meaning which I will discuss later, probably otherwise it will take some time. And the mapping of this, if you go to K tilde, and these are 2 points A tilde and B tilde, they are also symmetric if you apply the Mobius transformation. Okay. So we have actually used this property to solve our problem. So it is something like we have taken one spatial case in which this outer boundary is like, and this is the inner circle. So both are having center at along this real axis, you can say, and these are 2 points -1 and +1. And by using hit and trial, it is like it is possible you can check what could be a Mobius transform which actually transform this circle to in this kind of circle. So even if you see that these points -1 and +1, they are actually the fixed with respect to this Mobius transform. So if you substitute f -1, you will also get -1, f +1 is also +1. So this is one of the special case, and that came from the hit and trial, which does this part. Then what is remaining now, that we have this inside circle, the points P and Q, and this is also mapped under this Mobius transform in this way. So we want to leverage this symmetry principle, and we want to say that these 2 points, the image of these 2 points is symmetric with respect to this W is equal to 0. Okay. So basically we want Fp and Fq, they must be symmetric. So what we want, Fp and Fq, they must be equal with minus sign, because this is on the opposite side of the origin. So from that you will get this kind of expression, and this must have a solution for real solution for alpha. So basically this is a kind of quadratic equation, Okay, and indeed there exists a solution of it. So there is one theorem which says that if you have two non-concentric circles in the Z plane, so this is a circle center is at origin and the radius is 1, other circle is having center at lambda and the radius is mu, and it is possible to find a Mobius transformation such that you get two new circles in the W plane. They are having the radius like this. You can see they are centered now at origin, but their radius are different, and but you need to able to find the root of this equation. And one requirement here is that this Z is equal to minus beta does not lie in either of the circle, because then there is a problem. Okay, so this is one of the requirement, and this requirement actually went well with the practical application. So what is happening, we realize that when Z is equal to minus beta, this point lies in either of the circle. In that case, you will get this condition that your alpha will actually become exactly equal to plus minus 1, and in that case you will get these two kind of scenarios. Okay. But in our problem we are considering this scenario in which there is some gap between the two boundaries, and that is also required for the maneuverability of the robot, okay, and also for the safety, because this is all being done for the safety. So this desired circle must be little ahead from the outer boundary. So this goes well with that. So with this, now I will just discuss this interesting point that if you see the previous theorem, it just talk about what is the mapping of two circles in the other in the transform plane, but it does not talk about how the regions enclosed inside those circles will be mapped to the other plane. Okay. So this actually depends on the root of that quadratic equation which I discussed before, and if you find there are two roots, if you take the positive and negative sign of the discriminants of this quadratic equation, you will get two values of alpha, and we proved that for the smaller value of alpha, the interior and exterior mapping is preserved, but for the larger value of alpha, the mapping is actually reversed. Okay. So this is one of the theorems from our paper. So this is like the pictorial representation of the same. So this is our original problem. This is the desired stabilizing circle on which we want all the robot to move. This is the external boundary within which we want to constrain its motion or trajectories, and this is some outside region which is tending to infinity. So this basically represents the region. This is annular region between these two curves, and this is the region enclosed by the internal curve. So when you choose the smaller route, you will actually get two concentric circles, okay, the green one and the red one, and their region mapping is also preserved. You can see here, this outside region is like pink, and this is the annular region, this is the region inside this small circle. But what will happen if you take the larger route, the mapping will be reversed, and the outside region will go inside this region, annular region will be unchanged, and this inside region will go outside. So what happened because of that? So if you see only in the transform plane, the problem is actually can be put as the equivalent of two contrasting problems. One is trajectory constraining problem, in which you want all the trajectory to be bounded within this boundary, but on the other hand, in this case, what do you see that this like the outside region from the actual problem, it is coming inside, so you actually want to avoid this region. So now this can be casted as collision avoidance problem. And what is the interesting part here, that there exists only unique control law which solves both these problems and the actual problem in the original plane. Okay, so here this is the delta t, which is actually the difference between the two curves for different value of alpha s and alpha l. So this is like, so when we like want to solve the problem in the transform plane, we also need to transform the model. So that's what we have done here. So this is the model in the original plane, this unicycle model of the robot, and it is going into the transform plane. Okay. So one interesting point here is that this is also actually a complex number. So you cannot just directly transform the speed and you will get the speed in the other plane. It is not like that. what you can do using the Mobius transformation, you can only transform the positions, and then from position you need to obtain this kind of model. Okay, so these are the two models, and basically this is something similar what if I try to draw an analogy, that in classical control theory we have this frequency domain analysis in which we have a linear system, we are applying this sinusoidal input, and output also is a sinusoidal, right? But what is happening with the output, that there is there is magnitude is scaled, and there is also kind of phase shift. So the same thing is actually happening with these things here. So actually in this model, if you see that the velocity is also the scaled version of this velocity, and this angle is also like some shifted from this heading angle, and that is precisely coming from this Mobius transformation. Okay, so that is some of the interesting thing that is which is happening here. So now I will just talk about how we can find this control omega, and how from this control omega how can we obtain this actual control omega. So in this direction, I just want to obtain some crucial relation between the two positions and two heading angles, and then we can go to find the relation between two controllers. So one of the interesting point here that I want to tell, what happens, let's say in the actual plane where your problem is there, in the original plane your robot is moving in the clockwise direction, but if you see the same thing in the transform plane, then what will happen if you choose the small root of that equation, you will see that the robot is actually moving in the same direction, but the direction actually reverses if you choose the larger root. So like the exterior and interior relation exchange, the same way the direction of the motion of the robot also changes. So this proof we did by relating the two unit vectors in the plane, and then we proved this part. So now coming to this control law, so this is actually the control in the transform plane. Okay, so this is coming from the barrier Lyapunov function. This is basically the error in the transform plane, and this delta t is basically the separation between the two boundaries in the transform plane. So this is the control, and under this control, the robot, virtual robot in the transform plane actually stabilizes on the desired trajectory, and its its motion remained bounded. So these are some of the bounds. So what we prove, that with this control law, you can choose either of alpha as a smaller root or bigger root here. So with this control, what will happen, we have proved that this actually solves our problem in the real plane. Okay, in the real plane, we want the robot to move on this unit circle, so this is actually solving that problem, and also the trajectory bounds are maintained. And one interesting point here is that we also explored the inverse Mobius transform. So inverse Mobius transform in our case is coming in this way, so which may have a singularity at rho is equal to 1, but we proved that this alpha is cannot take value plus minus 1, so there is no like this is already always well defined. So we can actually establish relation using either Mobius transform or inverse Mobius transform. So there are like plethora of results that you can establish by using either Mobius or inverse Mobius transform. So this is like an interesting relation. This is relating two heading angles. This is the heading angle in the transform plane, and this is the heading angle in the original plane, and gamma, this chi is the phase shift which is coming because of the Mobius transformation, and it actually depends on the position and this Mobius coefficient alpha. So when you take its time derivative, you can actually establish the relation between the control laws. So that's what we have done here. So in this relation, we need to find what is chi dot. So the proof of this was very interesting, and like it actually took a lot of effort of us, and finally we got very simple expression like this. So this is actually our control relation. So I will not go into much detail because of the time constraint. So I will just simply come to this result. So this is for the single robot system. So here this is going on the desired circle, trajectories are bounded within this external boundary, error is going to 0, and we have this control plot, actual control plot for different value of roots, alpha s and alpha l, so they are also going to the desired value, although they have different kind of behavior, slightly different behavior for these values. And this is the motion of the virtual robot, you can say, in the transform planes. What is happening? In this case, when you are choosing the smaller route, the motion is like maintained, and in other case, when you are taking the larger route, it is moving in the clockwise direction. Here it is moving in the anti-clockwise direction. And this is like a collision avoidance problem. So this is like the circle is like obstacle that you have to avoid. So that's what it is actually happening. So these are some of the results in the transform plane. So so this is the work done with my PhD students. So thank you everyone. And if you have any question, you can ask me because I have already exceeded the time. So I also have like, so we are actually extending this work to multi-agent case. So multi-agent case, the problem is actually very interesting. Okay, we cannot. So I will just show you something that what is happening. You can see that these are the Capra robots, and they are actually moving on this desired circle, and their trajectory is bounded within the external sink. So you can see that as soon as the robots are coming closer to this red boundary, their speed is reducing a lot. You see this agent which is very far, and when it is coming to the boundary, it is automatically slowing down, slowing down. So we have also done this work for the multi-agent system, but we yet to communicate this part. Okay, thank you.
Okay. Thank you, Professor Jain, for the exciting talk. So we can take one question as, so audience, any questions? Yes, Gautam.
Presentation. So my question is on the arbitrary safe boundary condition. Yeah. So my question is on the arbitrary safe boundary condition, boundary geofencing. So sometimes it can happen that the robot is like on the near to the boundary of the geofence. At that time, it might not be possible to get a circle which actually, lies within the boundary itself, like the geofence boundary. In that case, maybe an elliptic kind of, extension of this problem can be explored. Is that something which has been discussed in, let's say, related to Mobius transformation, or it's just the circular transformation which has been discussed in the book?
Yes, so I think it can be extended to in a general setup. Only thing, what benefit we got using Mobius transform, this actually works only for circuits. Okay, but if you are talking about different shaped curve, then you need to look into some other aspects. Okay, so that is actually a complicated problem. Yes.
Okay, one more question. Yes.
My question is more basic. Thanks for the presentation. You explained so much. My question is more basic. How did you get that Lyapunov function? I was wondering about that.
So this actually, like when that time we came across one paper by KPT, so there this barrier Lyapunov function was there, and from that we got this idea, because when we want to meet some constraint on any system, you need to like change. So there is something which is also people are doing, that is control barrier function approach, but it also has its limitation because feasibility issues also arises because it uses this quadratic program framework. But we got this idea of barrier Lyapunov function, which also like by using that we can also restrict some of the constraint. So from one paper we got that idea.
Okay. Thanks, everyone.